All right, everyone, good afternoon. So thank you for coming to class today. And let's just, before we start with our lecture, let's just make sure we are all on the same page. Today is the 24th of February. Just some quick reminders for everyone. I'll take your homework 13 this Friday. You can upload it and take a picture, scan it, do whatever you need to do. It's practice after all, and I'll put in 10 points, so make that due this Friday. This Friday is the 26th. We're heading towards the end of February, so time is marching on. Work on quiz 2. So we will have a test coming up in March or so. So work on that. Don't wait till the last minute. So we will have a new lab this Friday. So make sure you come prepared for that. It's on rates of reaction. So you'll find the rate of a reaction. You will determine the rate law. There's videos, and you can check out the handout on Canvas. So make sure you do the lab. Come to lab this Friday and do the associated lab report. Anything else here? Lab, quiz, homework. Maybe start on homework 14. Okay, so all the problems that are assigned, I made videos of them to walk you through the steps, so that should be able to help you. So start homework 14 and get that on Canvas for your 10 points. And for those of you that paid the $30, make sure you do your clutch prep, and I'll give some extra credit, percentage points at the end of the semester. I got an email from them yesterday. There's 5 of you guys enrolled, and out of those 5, 4 are doing something. 5, the other one is not. So, not for the class, but more for you. I signed us up for it. Unfortunately, you have to pay money. And I'll give you some, like I said, extra credit at the end of the term. If you do everything, if you do from A to Z, all their little videos, all their little quizzes, all their little tutorials or whatnot. All right, so make sure you do that. Anything else? Am I missing anything? The lab report should already be due on intermolecular forces, so we will.
I'm talking about freezing point depression.
Yeah, the freezing point.
Yes, freezing point depression lab report is due. Thank you. I knew I was missing something. The lab report is due, and that lab report is on freezing point depression. Thank you, Joshua.
Good catch.
Good catch indeed. Yes. You want to put those points in, so make sure you do that lab report. Yeah, it is due, definitely, because we are at the end of that, 2 weeks. All right, so thank you, Joshua, one more time. And I think this is it. Anything else you guys can think of? Lab report, homework, a new lab this Friday. Continue working on the quiz. Turn in your homework. Start the new homework. Okay. Maybe another thing I want to put in here, this is for the end of the term since we are at the end of March. Make sure you turn in a lab notebook at the end of the term. Okay, if you need to know what goes into the lab notebook, you can see me. I have sample lab notebooks from last year. End of semester. All right, so this is what's on tap for this week and a little bit of next week as well. All right, so I will move on to chapter 14. We just touched the surface on Monday. The big key theme here on chapter 14 is a big K, capital K, and that is the equilibrium constant. Okay, so it's telling us which way a reaction will proceed. So So obviously, look for the arrows, right? Okay, look for the arrows. If you see a back and forth going arrow, okay, you're in a reaction that's at equilibrium. It's going to settle. Okay, will it settle like this, like this, like this? It could even settle 50-50. That would be an equilibrium constant of 1. Okay, but some equilibrium reactions are like this, or like this, or like that, or like this, you know. So it's going to settle. Okay, where it settles, it could be more reactants than products, more products than reactants. We measure that magnitude numerically. We have to put a number to everything, right? We measure that with K, capital K, and this is called the equilibrium constant. All right, so first thing here, you got to make sure your equation is balanced, and the number from the balanced equation becomes the power, okay, becomes the exponent. A lot of people miss this based on my experience. Okay, so you raise it to that appropriate power. Okay, C gets raised to that power, which is the number in front of the equation. All right? All right, so that's rule number 1. And rule number 2 here is you don't want to put solids or liquids in K. Okay, so let's write that down here. No solids or liquids in K. Okay, you're not going to put solids. A lot of people do this, and it's an error. No solids or no liquids. And equilibrium constant K. Just don't do it. Don't fall for that trap. Okay. One thing is these brackets represent concentrations, which is a big M, moles per liter. So solids don't have a concentration. Solids have a density, but they don't have a concentration. Liquids, it's sort of the medium in which the reaction proceeds. So if you take all the reactions that you do in your lab, excuse me, they're done in a solvent. The solvent is not doing anything. The reactions that are dissolved in the solvent, whether it's water or blood or whatever, the reactions dissolved in the solvent, that's where the chemistry is at. So the liquids, pure liquid is just a pure liquid. Okay, it's just the medium. It's just the basis for which the reaction is being undergoing. So with that in mind, just don't put solids and don't put liquids in here. Okay. So the only thing that really goes in here is gases. Okay. The only thing that goes in here are gases or concentrations in moles per liter, which is aqueous. I guess what I'm trying to say is the only states that you should worry about are concentrations, aqueous, or gases. All right, let's do some problems here. Going to page 2 now. All right, so just remember here, K is our equilibrium constant. It's capital K. It's quoted at a specific temperature. And another thing here, this may be something that everyone will like. It's unitless, so you don't have to worry about units. Okay. So there are no units in K. By the way, there's something else that has no units, and that is pH, that we will talk about in our next chapter, chapter 15 or so. pH and pOH also is unitless, and that's our next chapter. So don't worry about putting units with regards to K, equilibrium constant. All right, so here's some equilibrium reactions. So look at the arrow. Okay, I invite you to observe the arrow. Be very keen on this. Look at the arrows. And the arrows tell us that this reaction has some reactants left over as well as some products left over when it is all said and done. And here's our equilibrium constant. Okay, so where do you think this 2 comes from? Right there in the exponent. Where do you think this 3 comes from? Right there in the exponent. Right, and it's products over reactants. Each raised to the power. Each raised to the power. Each raised to the power of the coefficient. Once again, don't put solids, don't put liquids in there. So another thing I want to tell you guys is if you have gases, you can also express it as a pressure. Okay, so one interesting thing about gases, so you can express gases as a concentration. Gases can be expressed as a concentration. In this case, we're talking about moles over liter. Or expressed as a pressure. Okay, here it's atmospheres. Atmospheres, millimeters of mercury, whatever the units of pressure. Torr is another unit of pressure. And really that's what you see here. Okay, instead of concentration, we put pressure. Only for gases. Only for gases. Again, same rules apply. Okay, where does the exponent 2 come from? Products over reactants. Where does exponent 3 come from? Products over reactants. Okay, here it's just pressure, here it's concentration, right? Here it's just pressure, here it's concentration, only for gases. Only for gases. All right, so here I have it in all these different expressions. All right, so a word about subscripts. So here I have KEQ. Okay, that stands for equilibrium. But what I want to tell you guys is don't worry so much about the subscripts. Okay, because you're going to see we have a KP here, which means pressure. Okay. We have a KC. What do you think C stands for? Concentration. Okay, so C is for concentration, so the equilibrium constant will be in concentrations. There's something called a KW, which is the equilibrium constant for water. So you're going to see a lot of subscripts in this course. It's the same equilibrium constant, products over reactants. There's something called KSP. All right. There's something called KF. There's something called Ka, okay, for acid. The A stands for acid. There's something called Kb. It stands for base. So there's all these different Ks. Okay, so don't get yourself confused. It's the same thing, products over reactants. Okay. The P here is for pressure. This is for concentration. This is for water. This is for acid. This is for base. This is for something else. This is for something else. Okay, so it doesn't matter about the subscript. No matter what subscript you see, you can even see my name. Okay. It doesn't matter. It's the same equation that's going to apply, and the same rules, no solids or liquids that will apply. So K Vj, K Harper is looking there. Okay, it doesn't matter about the subscripts. Okay, it's this same thing. This same thing. Okay. This equation. This equation is called the law of mass action. So if you're studying for your, board exams or whatever, standardized exams, you'll see the term law of mass action. That's what this is called. Products over reactants, each raised to their coefficient, no solids, no liquids. So a bunch of different Ks, all will follow the law of mass action. All right. Kind of the same thing here. Unitless. Okay, this is another thing. I've seen students put units by K, and that's not correct. So no units on this equilibrium constant, capital K. Capital K. So let's do some examples here. So here we've got two gases. Look at our arrows. Okay, always look at your arrows. And we can do this as a Kc. The C stands for concentration. Concentration of NO2 squared. Divided by concentration of N2O4. Okay, you see that these are gases. And so we can also do a pressure. That's going to be pressure of NO2 squared divided by pressure of N2O4. Because they are gases. All right, so this value, I have it on the next page here. We looked this up in the book, or I looked it up in the book, and I got it as 4.63 times 10 to the minus 3, the concentration. Okay. Where did I get this? Okay, you just look it up. All right, you look it up from the book. So you can imagine you'll have all these different reactions. All of them have equilibrium constants. If the reaction is in equilibrium. Not all reactions are equilibrium. Some reactions just go straight to products. So here we just look up. Okay, also, I want to tell you that this is at 25 degrees C. Okay, if we're going to do this reaction at 30 degrees C, we'll have a different K. If we do this reaction at 40 degrees C, we will have a different K. So. All right, again, what is this telling us? Okay, which way does this reaction favor? Products or reactants? Okay, this is not 100%. This is a reaction that will not 100% go to products. Okay. And this is a reaction that will not 0% stay at reactants. Okay, there's going to be some level of concentrations where this will settle, and where it settles at is called the equilibrium constant for a specific temperature. So where do you think this particular equilibrium resides? Primarily on the reactant side or primarily on the product side? 10 to the minus 3. Reactants or products? This would be to the reactant side. So we would have, for this particular reaction, for this specific reaction, given the equilibrium constant, 10 to the minus 3, at this temperature, more of it will be on the reactants. More of it will be this way. Okay, just the number tells us. Okay, the number tells us it's going to be more reactants than products. Why more reactants than products? Because your K is much, much less than 1. Okay, so it's going to go this way, more reactants. Okay, this is reactants, and These are products. Okay, if K is equal to 1, okay, we are kind of right here. Okay, perfectly balanced if K equals 1. So this is what the equilibrium constant tells us, law of mass action. You kind of see that here, all right? Remember I gave you the example, if we have $1 million, are we moving forward or backward in life? Okay, we're moving forward in life, okay? Now K is unitless, so instead of dollars, we have no units. But if you have $1 million, you're moving forward in the reaction. If you have $1 million, you're moving forward in life. If you have an equilibrium constant that's 1 million, 1 times 10 to the 6th, you're definitely moving forward towards the products. K is equal to 1, no favor. It does not favor the products, does not favor the reactants. Some relationships between Kc and Kp. Remember, C stands for concentration, P stands for pressure. All right, so here's the relationship right here. I will give you this on the exam, so you do not have to concern yourselves with memorization. Just want to bring your attention to this delta N. Okay, delta N is moles final minus moles initial. Okay, so moles final minus moles initial. That is change in number of moles. Okay. Final number of moles minus initial number of moles, and that becomes an exponent. This R is your gas constant. Temperature is T in Kelvin. So I replaced R with 0.0821, and this is just more simplified, replacing R. Okay. And once again, here's our delta N. This, again, just to refresh ourselves, is being able to switch from Kc concentrations to Kp, or switching from Kp to Kc. Okay, from Kp to Kc, or from Kc to Kp, pressure and concentration, switching the equilibrium constants. So obviously this has to do with gases, because gases are the only state of matter that could be expressed as a pressure, correct? And gases are the only state of matter that can be expressed in moles per liter, a concentration, correct? All right. Once again, want to remind ourselves, we're going to see a lot of Ks. I'm going to teach you a lot of Ks throughout the next several weeks. But the law of mass action still holds. This still holds no matter what type of K we're talking about. Okay, no matter what type of K we're talking about, this still holds. No solids, no liquids. Okay, no solids, no liquids. And I give an explanation here why we put no solids, no liquids. If you want to go a little deeper, you can check that out. Otherwise, no solids, no liquids here. Okay? Please, no solids, no liquids. So again, I want to harp on this as much as I possibly can. There'll still be some of us in our class that will miss this. But if you're going to ask for an equilibrium expression, here it's going to be K Here's going to be K. You notice I have gases and two solids, so here Kc can be the pressure of CO2, Kp, excuse me, can be the pressure of CO2 raised to the 1 power, or I could write it as Kc, which is equal to the concentration of CO2, okay, because they're gases, pressure or concentration. Okay, why did I not do this? Concentration of CaO times CO2 divided by CaCO3. Why is this wrong? Right, very good, solids. So solids don't go in there. That doesn't go, that doesn't go. Okay? So finally, this is what you get. No solids, no liquids. So these are the correct answers for this equilibrium constant. Is it at an equilibrium? Yes, it is, because of the back and forth arrows. And then once again, no solids, no liquids in this expression. How about this one here? How about this reaction? We have here acetic acid. This is called acetic acid. This is called water. This molecule here is called the acetate ion. And this molecule here, you don't really need to know this until next chapter, but this molecule here is called a hydromonium ion. Okay. Sometimes this is called H+. Same thing. So this is an equilibrium, and we have aqueous species. Will aqueous species go in? Yes, they will. What will not go in? Okay, what will not go in? The liquid water will not go in. Okay, the liquid water will not go in. And so it's products over reactants. Products over reactants. Okay, no liquid, no solid. This is called an acid-base reaction. This is something we will talk about next chapter. It's an acid. Acetic acid is an acid. And what do acids do? They give away protons. And this will give a proton to water and in turn become the conjugate base acetate. And water takes that proton, it becomes hydromonium ion. I think we were having a discussion, Robert, after class about buffers. So this is an example of a buffer. Okay, it keeps the pH from going too high or too low. That's what a buffer does. And we have weak acids that in our body, in the cell, or wherever in chemistry, that can serve as buffers. All right, so we'll talk about that equilibrium in our next chapter. For now, what you guys need to know is this, okay? What you need to know is being able to write this out. Okay, so highlighted here is what we should be able to get. Why is there no Kp here? Why no Kp? There's no gases. Okay? There are no gases, so no Kp. Why is it Kc? These are all aqueous, yes, okay? All right, some differences between K and K. Okay, K and K, okay. First of all, lowercase k is what we call the rate constant. Remember this from our last chapter? And what we're studying now is the equilibrium constant. So the confusion is one is lowercase, the other one is uppercase. Okay, what's the point of lowercase k? Okay, the point is rate laws. And it's telling us how fast. Okay, instead of miles per hour, how much molar per second is consumed, or molar per minute, whatever the time. Equilibrium constant, capital K, in contrast, is which way the reaction favors, this or that. Okay, this or that. So just want to tell you two very different measurements. Okay, one is a lowercase k, the other is a capital K. All right, the equations are different. Okay, so this is the rate law that we've been talking to you guys about in our last chapter. You'll do this in Friday's lab. And this is the equilibrium constant that we're learning right now, law of mass action. Once again, solids and liquids have no business in our equilibrium constant. Right. There are some exponents. Here are the exponents in our rate law. Can tell us whether that reactant, it's all about decay now for this guy. It's all about decay. The exponents in a rate constant tell us whether the decay is zero order, first order, or second order. So we'll use that sheet on the exam for the rate constant. Here the exponents are the coefficients of the balanced equation. So balance equation. The coefficients of the balanced chemical equations. Another big difference here on the units, rate constant, the units are going to be different. You're going to have to calculate them each and every time fresh. Okay, that's a pain. That's an issue from some of our previous years. You know, they put a rate constant, but they don't put units. The units will vary. Okay, the units will depend whether the overall order is 0, 1, or 2. Okay. So the units will differ. Equilibrium constant, luckily and thankfully, there are no units. Okay, just like pH, there are no units. Okay, so don't have to put any units for capital K, the equilibrium constant. And then finally, there's something called the reaction quotient, which is something that is exclusively, it's called Q. It's called Q. And that is something that is exclusively has to deal with the equilibrium constant. And nothing to do with this. Reaction quotient Q has everything to do with the equilibrium constant. And I'm going to teach you something called the Gator rule a little bit later on, if not today, on Friday. So Q and K has to do with the Gator rule. So we'll learn that soon. Don't have to worry about Q here. All right, so practice. Let's write some of these out. All right, look at our arrows here. Okay, always look at your arrows. You always have to have that I for the reaction arrow. And we'll do a KC first. Okay, our KC, the C stands for concentration. It's going to be the concentration of O2 times, right? Products over reactants times the concentration of NO2. What do we need to raise that to? 4. Very good. Raised to the 4th power. All of that divided by the concentration of N2O5. And we raise that to what power? 2. Okay, so that is the law of mass action in effect. Because these are gases, I want you to realize that because these are gases, we can also express this as a Kp, which is pressure. So let's do that. Depending on the problem, what you see, you can also get pressure. So the Kp is going to be the pressure of O2 divided by pressure of O2 times the pressure of NO2 squared, to the power of 4, divided by the pressure of N2O5, and we square that. Okay, so just be aware, because of gases, we can either do a Kp, standing for pressure, or Kc, standing for concentration. Okay, just be aware of that. All right, let's do another problem here, everybody. And this time we'll put some numbers in. All right, we got a reaction here. Check your arrows. Okay, back and forth means equilibrium. And at 74 degrees, notice everything is temperature dependent. We specify these things at a specific temperature, in this case 74 degrees. At 74 degrees we have the concentration of CO as that, concentration of Cl2 as that, COCl2 as that. Calculate the equilibrium constant. Calculate the equilibrium constant Kc. My goodness, all these years, and every year there's a new mistake I find. Every year, something new. Isn't that something? All these years and it has just gone by. Okay, it's the equilibrium constant, not the rate constant. Definitely, if you have your notes, okay, because I made a big deal. Rate constant is lowercase k. Equilibrium constant is capital K. Okay. All right, so we got our concentrations, we got our temperature, and these are equilibrium concentrations, right? How do we know? How do I know these are equilibrium concentrations? The problem tells us they're equilibrium concentrations. Okay, if these are not equilibrium concentrations, then we use something else, okay? But because they tell us it's equilibrium concentrations, we can plug it into the equilibrium expression. And the equilibrium expression is this. For concentration is going to be products over reactants. Each raised to the coefficient. Make sure this is balanced, and it is balanced. All right, so these are equilibrium concentrations. So now, because these are equilibrium concentrations, all we can do is just put them in, plug them in. Okay, so COCl2 is 0.14. Okay, no units necessary. CO is 1.2 times 10 to the minus 2. And then Cl2 is 0.054. And doing this on my calculator, I'm getting, you can double check my work, I'm getting 216. 1, 2, 1, 2, 1, 2. So 216. Right, so don't forget this is unitless. If I wanted it 2 sig figs, 2 sig figs, 2 sig figs, actually if you want 2.2 times 10 to the 2. Okay, it's the same thing, but this bottom answer is more towards the significant figures, having it the same number of significant figures as the problem, but you know, this or this will be fine. If I don't specify significant figures, you don't have to worry about it. This is good enough. Which way will this reaction proceed? Product side or reactant side? Which way when this reaction is done? Correct. Products. All right, consider this reaction at 395 Kelvin. And look at our arrows here. All right, the partial pressure of each gas is 0.265 atmospheres. Calculate Kp and Kc for this reaction. All right, so Kp is going to be products over reactants. So pressure of H2S times pressure of NH3. Is it divided by pressure of NH4HS? Divide this by that. Yes or no? No. Why is that? Because it's a solid. Okay, so done. Right? Everyone see that? No solids. So products over reactants. This is a solid. Has nothing to do with our expression. The partial pressure of each gas is 0.265. Let's assume this is equilibrium, that this reaction has settled. So if this is at equilibrium, we'll just put the 0.265 here of each gas. So those are our two gases. 0.265 squared is 7.0 times 10 to the minus 2. Again, we don't worry about units. And just as a reminder, okay, no NH4HS because it's a solid. Let's do Kc now. Here is our equation, and I'll give this equation on the exam. The equation is Kp is equal to Kc times RT. The RT is raised to the power of delta N, change in the number of moles. What is our change in the number of moles? Okay, so products, we have 1 mole of gas plus 1 mole of gas is 2. 2 minus the 1 mole of solid. We have 1 solid going to 2 moles of gas. So 1 plus 1 is 2. What's 2 minus 1? 1. So delta N here is 1. Kc we already figured out here as 7.0 times 10 to the minus 2. R is 0.0821. Okay, I'm not going to put units because K has no units. The temperature T, what is our temperature T? It's 395 Kelvin. And all of that raised to the power of delta N, which is 1. Okay, so that is what... sorry, my bad here. Kp is equal to 7.02. 7.0 times 10 to the minus 2 equals Kc. R is 0.0821. I'm not going to put units here because it's unitless. Temperature T is 395. And all of that is raised to the 1 power, and delta N is 1. All right, so we will isolate Kc. Kc is equal to, I'm going to take this and divide it by the 7.0 times 10 to the minus 2. So 7.0 times 10 to the minus 2 divided by 0.0821 times 395. And I am getting, as my answer here, 2.17 times 10 to the minus 3 for Kc. So we have our Kc here, utilizing this equation, and we got our Kp here, utilizing the law of mass action. The law of mass action, products over reactants, is how we got Kp. All right, couple of final words here. Where will this reaction favor, left or right? 7.0 times 10 to the minus 2. Where will it favor, left or right? Reactants or products? Reactants. So this favors the reactant side. Okay, look at the magnitude of this. So this favors reactants. Okay, talking about gases. What about if you're talking about concentration? Which way will this favor? Reactants or products? 10 to the minus 3. Reactants or products? Still reactants. Okay, 10 to the minus 3 is still will favor the reactants. So this is a problem where we calculated Kp, and then from that Kp, we were able to get Kc utilizing this equation. And I'll give you this equation on any exam, so you don't have to worry about that. Gases, pressure or concentration? Gases, concentration or pressure. Okay, the equilibrium constants are shown here. So we will start again on Friday. We will go to the next part. And see you Friday, and have a good day, everyone. So Friday we'll talk about the Gator rule. And we will talk a little bit more about equilibriums. Yeah. Another thing we will talk about on Friday and then move on into next week will be ice tables. So ice tables, generally people have a hard time dealing with it. So check out some videos on ice tables or use Clutch Prep and see what they have to say about ice tables. Anyways, that's something that's going to come to Friday and then next week.